Second lecture. This is a long chapter, so it's going to be in multiple parts. Our sun and the nearby stars are all part of a vast collection of stars called the Milky Way galaxy. For a long time, it was thought that this was the whole universe. It was only in 1924 that the American astronomer Edwin Hubble demonstrated that ours was not the only galaxy. There were, in fact, many others with vast tracts of empty space between them. In order to prove this, he needed to determine the distances to these other galaxies. We can determine the distances of nearby stars by observing how they change their position as Earth goes around the Sun. But other galaxies are so far away that unlike nearby stars, they really do appear fixed. Hubble was forced, therefore, to use indirect methods to measure the distances. Now, the apparent brightness of a star depends on two factors: luminosity and how far it is from us. For nearby stars, we can measure both their apparent brightness and their distance, and so we can work out their luminosity. Luminosity, this is my own addition, is really the amount of light that a star gives to a large extent. I think that's what it means. Conversely, if we knew the luminosity of stars in other galaxies, we could work out their distance by measuring their apparent brightness. Hubble argued that there were certain types of stars that always had the same luminosity when they were near enough for us to measure.
I have a question again. Why are you recording this?
No,
keep it in the recording,
I know. Just because I think it's.
Yeah, but where are you gonna put it up? Like,
I'm
what
not,
is the
just
use
to family, just to family and friends.
You're saying it in an American accent. You could at least say it in Tamil.
என்னடா சொல்லணும் நீ இந்த மாதிரி பேசுற இல்ல
Like நம்மளோட சன்னன் சொல்லுவ
சரிடா பட் நம்ம படிக்கிறது வந்து நம்மளுக்கு மாத்திரம் எதுக்கு இருக்கட்டும் நிறைய பேர் கேட்கலாமேன்ட்டு அவ்வளோதான் மெயின்லி நம்மளோட ஃபேமிலி அண்ட் ஃப்ரெண்ட்ஸ் தான்
Yeah, but our family is like
okay, this is pointless discussion. Nobody would want to listen to this, okay?
I know, I'm just making something funny, okay?
No. Okay.
Hey, I'm
now
a
back to
sarcastic kid. My name's Sokka.
Back to the reading. Conversely, if we knew the luminosity of stars in other galaxies, we could work out their distance by measuring their apparent brightness. Hubble argued that there were certain types of stars that always had the same luminosity when they were near enough for us to measure. If, therefore, we found such stars in another galaxy, we could assume that they had the same luminosity.
I think we already read that.
Actually, this part, again, my own addition, I don't know how these assumptions can be made, but I'm sure they did it correctly, but it's kind of not very clear here, okay? But anyway, let's just go ahead. Thus, we could calculate the distance to that galaxy. If we could do this for a number of stars in the same galaxy, and our calculations always gave the same distance approximately, we could be fairly confident of our estimate. In this way, Edwin Hubble worked out the distance to 9 different galaxies. Is only one of some. How many? Let's see. One of 100,000 million that can be seen using modern telescopes, each galaxy itself containing some 100,000 million stars. My goodness. We live in a galaxy that is about 100,000 light years across and is slowly rotating. The stars in its spiral arms orbit around its center about once every 100 million years. Our sun is just an ordinary average-sized yellow star near the outer edge of one of the spiral arms. We have certainly come a long way since Aristotle and Ptolemy, when we thought that the earth was the center of the universe. Stars are so far away that they appear to us to be just pinpoints of light. We cannot determine their size or their shape. So how can we tell different types of stars apart? For the vast majority of stars, there is only one correct characteristic feature that we can observe: the color of their light. Newton discovered that if the light from the sun passes through a prism, it breaks up into its component colors, its spectrum, like in a rainbow. By focusing a telescope on an individual star or galaxy, one can similarly observe the spectrum of light from that star or galaxy. Different stars have different spectra, but the relative brightness of the different colors is always exactly what one would expect. My son just so I need to start once again. By focusing a telescope on an individual star or galaxy, one can similarly observe the spectrum of the light from that star or galaxy.
My dad decided.
Different stars, the relative brightness of the different colors is always exactly what one would expect to find in the light emitted by an object that is glowing red hot. This means that we can tell a star's temperature from the spectrum of its light. Moreover, we find that certain very specific colors are missing from star spectra, and these missing colors may vary from star to star. We know that each chemical element absorbs a characteristic set of very specific colors. Thus, by matching each of those which are missing from a star spectrum, we can determine exactly which elements are present in the star's atmosphere. In the 1920s, when astronomers began to look at the spectra of stars in other galaxies, they found something most peculiar. They were the same characteristic sets of missing colors as for stars in our own galaxy, but they were all shifted by the same relative amount towards the red end of the spectrum. The only reasonable explanation of this was that the galaxies were moving away from us, and the frequency of the light waves from them was being reduced or redshifted by the Doppler effect. Listen to a car passing on the road. As the car is approaching, its engine sounds at a higher pitch, corresponding to a higher frequency of sound waves, and when it passes and goes away, it sounds at a lower pitch.
Hey, I think we've already listened to this before.
The behavior of waves is similar. Indeed, the police made use of the Doppler effect to measure the speed of cars by measuring the frequency of pulses of radio waves reflected off them. In the years following his proof of the existence of other galaxies, Hubble spent his time cataloging their distances and observing their spectra. At the time, most people expected the galaxies to be moving around quite randomly, and so expected to find as many spectra which were blue shifted as ones which were red shifted. It was quite a surprise, therefore, to find that the galaxies all appeared red shifted in every direction. That's pretty amazing. Every single one was moving away from us. More surprising still was the result which Hubble published in 1929. Even the size of the galaxy's redshift was not random, but was proportional to the galaxy's distance from us. Or, in other words, the farther a galaxy was, the faster it was moving. And that meant that the universe could not be static as everyone previously thought, but was in fact expanding. The distance between the different galaxies was growing all the time. The discovery that the universe was expanding was one of the great intellectual revolutions of the 20th century. With hindsight, it is easy to wonder why no one had thought of it before. Newton and others should have realized that a static universe would soon start to contract under the influence of gravity. But suppose that instead of being static, the universe was expanding. If it was expanding fairly slowly, the force of gravity would cause it to eventually to stop expanding and then to start contracting. However, if it was expanding at more than a certain critical rate, gravity would never be strong enough to stop it, and the universe would continue to expand forever. This is a bit like what happens when one fires a rocket upward from the surface of the Earth. If it has fairly low speed, gravity will eventually stop the rocket and it will start falling back. On the other hand, if the rocket has more than a certain critical speed, about 7 miles a second, gravity will not be strong enough to pull it back, so it will keep going away from the Earth forever. This behavior of the universe could have been predicted from Newton's theory of gravity at any time in the 19th, 18th, or even in the late 17th century. Yet, so strong was the belief in a static universe that it persisted into the early 20th century. Even when Einstein formulated the general theory of relativity in 1915, he was sure that the universe had to be static. He therefore modified the theory to make this possible, introducing a so-called cosmological constant into his equations. This was a new anti-gravity force which, unlike other forces, did not come from any particular source but was built into the very fabric of space-time. His cosmological constant gave space-time an inbuilt tendency to expand, and this could be made to exactly balance the attraction of all the matter in the universe so that a static universe would result. Only one man, it seems, was willing to take the general relativity at face value. While Einstein and other physicists were looking at ways of avoiding general relativity's prediction of a non-static universe, the Russian physicist Alexander Friedmann instead set about explaining it. The next section is Friedmann models, and we will continue this at a later time.